Now we get to put all the variables back together. So the solutions, the solving that we did, was with each variable separately. So to put them back together, we remember that u of x and t equals x of x times t of t. So now remember that x had a whole bunch of different solutions that were the Fourier sine eigenfunctions, and each one of those Fourier sine eigenfunctions went with its own eigenvalues for lambda n. So here's what that solution then looks like. It's a bunch of different terms where here's the sine, the solutions with x were the sine eigenfunctions in x, and here's our exponential that was the solution for t. So notice this has x only, no t. This has t only, no x. Notice that the lambda we just plugged in. Lambda, remember, is k squared, and since k is the n pi over l, lambda is the square of that, n squared pi squared over l squared. So this is a lot of stuff in that exponential. It's just a lot of constants. The idea is it's still an e to the minus t with a bunch of other constants in it. So there's the t part and the x part. And since there are one of these functions for n going from 1, 2, all the way up to infinity, the solution, using a principle called superposition, the solution would be a constant times all of them, or any linear combination of all of these. The solution has an infinite basis. So a constant for all of these things. Now here's the cool thing, is we still have this constant. We used the boundary conditions to find the eigenvalues. We then use just like in ODEs, we will use the initial condition to find the arbitrary constants for each one of those terms in the Fourier series. And the way we do that, and you notice we've written it as g subscript n, that's because it turns out that these are exactly the coefficients, or the Fourier coefficients of that initial condition function g of x. Notice that if you plug in t equals t0, plug in the time for the initial condition, this is 0 up here, and so e to the 0 is 1. So at t equals t0, all of this cancels, or it's just 1, and so we get exactly the Fourier coefficients, the Fourier sine series of the initial condition, which is g. So in t equals t0, u of x t equals g, which is gn sine of n pi over lx. So then, here's a reminder, in case we forgot from chapter 5, how to find Fourier coefficients. If g has exactly this Fourier sine series representation, there's all the sine functions, and they have those coefficients, then Fourier's trick was to take both sides of this equation, multiply by sine of m pi over x, like some different from n, m pi over x, both sides multiplied by that should have a g of x, and integrate from 0 to L. So if we do that to both sides, here we get the integral of all these different terms, so n goes from 1 to infinity, and they're all multiplied by sine of m pi over lx. And remember, since these are orthogonal, and this is an inner product, a lot of them, all of them but one, become 0. And so this whole infinite summation is just zeros except for this one term, when n equals m. And when n equals m, that's sine of m pi over lx times itself, the integral of sine squared. So that integral of sine squared is not 0. So again, when n and m are different, that's all 0. This is when m equals n, that's not 0. And the integral of this from 0 to L is L over 2. We did that integral also in chapter 5. And so if we want to solve for these coefficients, gm, we just multiply both sides by 2 over L. And so you see that's the last equation in this section. Those constants, gn, on your handout it's n, here it's m. but the constants are 2 over L times the integral of g with that sine function.